Good morning, friends. I am Dr. Dwivedi from Institute of Aeronautical Engineering, Hyderabad, India. I am going to take the course which is Aircraft Stability and Control. Today, I am going to take lecture number 24, which is Aircraft Handling Qualities. Going with my topics, these topics which I am going to cover today, following topics to be covered in this lecture: revision of stick fixed and stick free expressions, derivation of stick force Fs, stick force gradient, that is dFs by dV, where Fs is a force, stick force, and dV is a velocity, change in velocity. In this topic, we are going to answer following questions. What is the difference in stick fixed and stick free? How to assess the effect of stick force gradient? Need of handling qualities of aircraft. Okay, so these points I am going to discuss in today's lecture. In my previous class, I have discussed about the hinge moment. In hinge moment, I have also discussed that if the deflection of elevator in float, that is equal to the required deflection, that is delta E naught plus d delta E by dCl trim into CL trim. If both are equal, then Fs will be 0. It means the floating and the opposite to the floating, if both are neutralized, there will not be any force. And I have also shown that we have to use the horn balance to counter this phenomena, so that pilot will not experience any stress, he will not feel any force in the stick. Okay, this we have discussed in the previous lecture number 23. Now today I am just going to revise again, and these topics I have already covered in some of the classes, the previous classes. I am going to again revisit, so that it will give some insight into the equations which we have already done. So recalling previous mathematical expression on the neutral point of the stick fixed and stick free conditions. For the control fixed neutral point, means stick fixed. Stick fixed means what? Pilot will give some angle and it will remain there. It will not vary. When we talk about the stick free, pilot will not give, due to aerodynamic forces, the lift will, or the aerodynamic forces will take the control to its own way. That is called the float or stick free. Till now we have discussed most of the cases stick free only. But to discuss about the handling quality, we should understand about the floating tendency or stick free condition also. Okay, to have only elevator deflection, stick free is sufficient. But when we talk about the pilot, how much pilot force is going to apply, that time we have to express about Fs. And that time stick free cases are considered. Okay, so here we have seen that neutral point and not stick fixed, we have already derived in the previous classes, that is x bar AC wing minus dCm by dCl stick free plus CL alpha T by CL alpha W VH n neta T 1 minus d epsilon by d alpha. For the control free cases, what will be the neutral point? So here the neutral point, we have to make a prime here, this prime. So this n naught prime free is equal to XACW. This is same here, minus dCm by dCl Fs plus here. These two parameters are same for the fixed and for the free cases. But here the changes will come in the third. Here CL alpha T will be CL alpha T prime. This only one parameter will change. Only CL alpha T parameter will be here prime VH N eta 1 minus D epsilon by D alpha. So only one parameter. What is that parameter? That is the CL alpha T. The CL alpha T of the stick fixed case and the CL alpha T of the stick free case is little variation we are going to face. So we also know the relation of stick free and stick free CL alpha T. We have derived this thing in our previous classes that CL alpha T prime, that is, it is a free case here. Free case is equal to CL alpha T, it is a fixed case 1 minus tau CH alpha T by CH delta E. One tau term is added here. And you know that what is this tau? Okay, we have already discussed about this. Tau is varying with SE and CE. Means elevator area and elevator chord. It is varying with this. We have already shown one plot like this. That this is the tau and this is the SE and by CE. So here it is going like this. And maximum value is 0.8. Average value is 0.4 for the tau. Okay. So this we have discussed in unit 2 and all. So we need to establish what is the value of CL alpha T prime in equation 3 from equation 2. So if we subtract this thing, so here N naught minus N naught prime, this minus this. So what we will get here? We will get CL alpha T by CL alpha wing VH N neta T 1 minus D epsilon by D alpha tau CH alpha T by CH delta E. This we got here. Okay, so now we can make it here. Very good expression will come. This NO, we can make NO minus XCG, and for this NO prime, we can make plus XCG minus N naught prime. Okay, so minus XCG plus XCG. No variation, na? It is balanced. But you know that NO minus XCG is minus DCM by DCL, and this is the fixed, and here XCG minus is DCM by DCL free. So this is case of the free and this is case of the fixed. Okay, so that is the variation. So now minus DCM by DCL fixed is equal to, we know that it is a minus SM, there is a static margin. So rearranging the previous equation, we can get that DCM by DCL free is equal to DCM by DCL fixed plus CL alpha T by CL alpha wing VH neta T 1 minus D epsilon by D alpha tau CH alpha T by CH delta E. So here the value of CH alpha T and CH delta T is negative. Okay, this value is negative. And here for the fixed case, DCM by DCL is greater than 0 for the wing. Okay, so as this thing is negative and this CL alpha T by CL alpha wing is always negative. So this is the, it is a positive here. It is a destabilizing. So it is a positive, it is a negative, and it is also negative. So here DCM by DCL free is less stable compared to DCM by DCL fixed. Very, very important results we are going to get that DCM by DCL free means the margin, static margin, DCM by DCL free is less stable compared to DCM by DCL fixed. So DCM by DCL free is less stable. Okay, so we can see that this DCM by DCL free has got the less stability. So if the elevators are floating and they are floating in the real case, so this will create your aircraft as a less stable compared to which we have derived already in fixed case. Okay, that the result which we have got. Now I am going to discuss about the next topic, which is stick force and its gradient. So stick force, we know that Fs. Okay, so how we have to calculate this thing, and in this also we will get the one new component and its function, which is a trim tab. Okay, this is we are going to discuss in this topic. In an unaccelerated flight, the stick force Fs and stick force gradients are important parameters to assess handling qualities of the aircraft. So this Fs is very important for handling quality of the aircraft. If aircraft is flying at trim speed, that is called V trim, and if this V is less than V trim, V is less than means the aircraft is flying, just I have given the number. If the aircraft speed V is 90 meter per second and the V trim is 100 meter per second, a pull force required. Very important. I think so many of us, we don't know that if the trim speed is 400 kilometers per hour and your aircraft is flying at 350 kilometers per hour, then what we have to do? We have to pull the stick, pull towards the pilot. Okay, so we have to make stick, we have to put the stick up towards the pilot. And if the aircraft speed is more than the trim speed, assume that again here it is 100 meter per second and you are flying, you want to fly at 120 meter per second, then how you will fly? You have to put your elevator forward, push. A push force required for increased speed. Okay, very important. I think some of you may not know this parameter. So if you want to fly more speed, you have to pull, you have to push. If you want to fly at less speed than the trim, then you have to push. So a force is needed to fly the aircraft if not flown in trim condition, because aircraft is designed for the trim condition. If you want to fly out of the trim condition, then pilot has to take some action, and if pilot is taking some action, he has to apply some force. So if the aircraft is flying with a less speed than the designed trim speed, then he has to pull it towards the pilot like this. And if the speed of the aircraft is more than the trim speed, then he has to push away. Okay, these are the concepts. To have the aircraft fly without pilot force. So if he is applying this thing, and so he cannot hold like this. So we need some device. That device is called the trim tab. Because once he has reflected, push or pull, but he cannot hold like this for a long time. Because he has to always apply this. His hand will be tired. So a small device which is called the trim tab, this trim tab is used, and this trim tab will solve the problem, and pilot will fly hand free. He will not use, hands will be off. He will just adjust, and then he will adjust the trim tab, and aircraft will fly without applying any force of the pilot. Okay, this you can see here. This is the diagram here. This is your horizontal tail. Here is the elevator, and this is the trim tab. Okay, so here if you see here CM and here it is a CL. This is your condition. I have given 100. So if you want to fly in a more speed, so more speed means CL will be reduced, and in the less speed CL will be increased. Okay, so if you want to fly in this, then you have to push. You have to push. If you want to fly in this, okay, you have to pull. Okay, so here is the positive. So just at 120 means at higher speed, you need the positive CM. But at the lower speed, you need negative CM. Okay, so like this, we can vary. So now we have to derive the equation for the stick force, and it is Fs. So this we can see here that let us develop a stick force term Fs. Here you can see this is the stick here, and pilot is holding here, and this is from here to here. It is a distance from this hinge point to the application of the force by the pilot, and from here it is going to this side, okay, and it will apply here. So if it is applying, moving to this side, it will go down, okay. So hinge moment will be developed in this direction, okay. It is going down. So here this, you can see that this is the deflection ds in this, from here to here it is a ds, and this is the ls. So you can see that ls into work done, ls into ds by 2 means average, into fs. Fs is the force applied, force into distance, okay, is equal to here hm into delta E. Here it is a delta E is deflection, and it is also average. We are taking 2. So this 2 and 2 is abolished. So Fs is equal to Hm delta E divided by Ls delta S. Okay. So Ls is what? It is a distance from force to this hinge point, and ds is a distance from how much it is traveled from initial condition. Okay. So this distance, so we can calculate the force Fs is equal to Hm delta E Ls by del S, and this is called the G. This term delta E by Ls by ds is called the G, and G is known as the gearing ratio, and this gearing ratio is called delta E by Ls by ds. You know the gear ratio in lever, it is a leverage of the this control rod. So here we can see that for a positive Fs means push. Positive Fs means push, the Hm will be anti-clockwise. Okay, if you are pushing here like this, it will be anti-clockwise, it will be in this direction, and for the pull it is in this direction. Okay, so Fs, this will come minus GHM. Okay, so this Fs, the sign is always opposite. So if it is the positive, it will be negative. If it is the negative, it is the positive. Okay, so here we can see that Fs is equal to minus GHM. So if we plot the Cm versus Cl, we can get this is the your trim condition of Cl. Let's at Cl1 is equal to 100 meter per second and Cl trim is 120 meter per second. For lift is equal to weight, means it is a trimmed condition. If Cl2 is less than Cl1, okay, if Cl2 is less than Cl1, so alpha 2 will more needed. Okay, so if Cl2 is less than the Cl1, more angle of attack is needed. So alpha 2 is greater than alpha 1, so delta 2 is greater than delta 1 as shown 2 in the diagram. Okay, so it is very important that for the lesser Cl, we need more angle of attack. Okay, so here Cl2 is less than the Cl1, so here we need alpha 2 is less than alpha 1, but delta 2 is greater than delta 1. That we have to understand. Now, the question is how much stick force Fs is needed by the pilot. How much force pilot is required to put on the stick. In stick fixed case, it was done by elevator deflection delta E. I told you for stick fixed case, we don't need the pilot because it is self. It is automatically, you just fix it and it will behave. But in the real flying, pilot is doing. So how much pilot force is required? It is mandatory to understand. So in stick fixed case, how much elevator deflection delta E was required? So this required was delta E is equal to delta E naught plus d delta E by d Cl trim into Cl trim. This was the case. But here it is not so. But for the stick free case, stick force Fs by pilot is needed. So this Fs is equal to minus GHM. Just now we have derived. And this hinge moment, HM is equal to what? It is half rho V square E. E means elevator. Half rho V square is what? It is a dynamic pressure into area into chord length into CH. It is a hinge moment coefficient. So Fs required is equal to minus G half rho V square E SE CE CH. So Fs required is equal to minus G Q. This is called the Q, NT, SE, CE and CH. So how? So this half rho V square E we can write is equal to half rho V square Fs into, so here it will be Q into NT. Okay. So here half rho V square E into NT, and so here half rho V square E by half rho V square F, this is the NT. So we have mentioned here NT. So here Fs is the stick force required to be applied by the pilot. So this much you can calculate. If you know the G, if you know the Q, if you know the NT, SE, CE, CH, you can find out how much force is required. So Fs positive is push and Fs negative is pull. So here I have shown here. If you can see here, it is a pull. If I am putting my side, it is a pull. If I am that side, it is a push. So this is the push and this is the pull. So pull is negative and push is positive. So this much force is required. Fs is equal to minus G Q neta T SE CE CH. So now we have to find out hinge moment coefficient, because in the previous equation we got CH. So how to find this CH? This CH is equal to CH naught plus CH alpha T into alpha T plus CH delta E into delta E plus CH delta T into delta T. So this delta T is a trim tab. Here we are not considering for this case. So here alpha T, we know that it is alpha W minus epsilon minus IW plus IT. Where alpha W is a wing setting angle, epsilon is a downwash angle, IW is a wing, alpha W is a angle of attack for the wing, and IW is a wing setting angle, and IT is a tail setting angle. This we have so much, we have already done for this. So we got that here alpha T is equal to alpha W 1 minus d epsilon by d alpha minus epsilon naught minus IW plus IT. Okay, here epsilon is equal to epsilon naught plus d epsilon by d alpha into alpha W. We have put this value and we have done so many times before also. So here alpha W is equal to alpha W here, this is equal to CL by CL alpha W plus alpha naught. Okay, so CL is equal to CL naught plus CL alpha into alpha. CL is equal to CL alpha, alpha W minus alpha naught. Okay, so here this, we can see a very interesting result here, that at positive alpha, here tail plane, it is alpha, and elevator is positive deflected, then it will give a force upward and a nose down HM will be there. It will try, it is called the nose down HM. So if CH alpha T is less than 0, if CH alpha is less than 0 or negative, and CH delta E less than 0 or the negative, in this case, both are the negative. Okay, in this negative sign, nose down. If your tail is going up, so what we have to do here? If we fix a trim tab here, just you see here, it is going upward. Here alpha 0 is a negative. Trim tab, if it is going up, moment will be in this direction, okay, because lift is, force is in this direction. But here it is going down, it will make in this direction. So moment of this elevator and moment of this tab, both are countered, and there will not be any net force, and force will be removed. So a negative sign, nose down, delta T, tab angle, positive needed for delta E, minus delta E to trim the Fs. So here it is a minus delta E, but here it is a plus delta T. So for the minus delta E means it, when the elevator is going up, it is called minus. We need tab to go down, means tab should be positive. So in this way, the moments are countered. I think it is clear now. So now we have to find out the stick force gradient. dfs by dv. So fs is equal to k half rho v square. Okay, k half rho v square a plus ch delta t into delta t minus k w by s ch delta e by cm delta e dcm by dcl free. This we have derived in 4-5 classes before. Okay, so here now if we differentiate df by dv, we will get k rho v a plus ch delta t into delta t. In this, if delta t is positive, if this delta t is positive, so what is the meaning of delta t is positive? Means going downwards, trailing is going downwards. This case, okay, here is delta t is positive. Okay, here it is shown. So fs will be positive, or push force is getting. Okay, so here if delta t is positive, so a positive for fs will be positive, or we have to push the stick. So if delta t is positive and v increases, so more and more positive force is given by the tab to nullify. There will be a point where net fs will be 0. This ensured by the trim tabs, which gives in equilibrium. Okay, so what will happen? Just you can see here in this plot fs versus v. So here it is initial condition. Here when elevator is going up, trim tab will go down. So as you increase the velocity, this angle of tab will also increase, and here also when the elevator is going down, tab will go up. The net force here of tab and the elevator will be balanced, and your fs will be 0. Okay, so that is the objective of the trim tab, and aircraft will be in the trimmed condition. Forces to trim. So now again fs, the same equation, and if you make this as a 0, okay, so we will get here fs is equal to k half rho v square a plus ch delta e delta t minus k w by s ch delta e by cm delta e dcm by dcl free is equal to 0. If you make this thing, we will get here that ch delta t here, ch delta t into delta t, we will get 2 w by s rho v square trim ch delta e by cm delta e dcm by dcl. Okay, we will get here, putting the value equation 2 from equation 1, we will get that fs is equal to k w by s ch delta e by cm delta e dcm by dcl free v square by v square trim minus 1. So if we differentiate dfs by dv, then we will get the force gradient. So this force gradient, if you see here, this v will be v by v square, because, and this 2 will come here. So 2k w by s ch delta e by cm delta e dcm by dcl free v by v square trim. So if dfs by dv is greater than 0, so now if we plot this, then what will happen? So this we can see here, that we can see by the plot here that if the aircraft is flying at v trim, fs is equal to 0. This you can see, this is the v trim here. If you are flying in this, fs is here, fs is 0. But when flying less than the v trim, okay, this is the, if you are flying somewhere here, it is a less than the v trim, 0.1 and 2, a pull force, it is a negative. Okay, it is a negative. A pull force is required. If you are flying at lesser speed, you have to pull the stick. And when you are flying to higher speed, just this is the 3 and 4, and this is the 2 and 1. So if you are as a less speed, you need the pull force or negative force. If you are flying at a higher speed, you need a push force or the positive force is required. Okay, it is very important results for this. So if df by dv is high gradient, like in this one, it requires high forces to trim the aircraft. if this gradient df by dv is high, like here plot 1, so high forces are required. If like this plot 2, lesser forces are required. So these things, two very nice results we have got. If you want to fly at higher speed, we need the push the stick, means we have to make stick forward. And if you want lesser speed than the trim, we have to pull the elevator. However, if you want to make less force, if you want to apply, then the slope of df by dv, it should be less. Then we can get the lesser effect. So here we have to, in the next class, we are going to discuss about the reversible control, then difference between CH alpha T and CH delta E, and next is trim types. Because here we have not done much about the trim types, but here we got some idea that if we have the trim type, the Fs will be 0. So the objective of trim type, that pilot should not use always force, and it should, so this will be discussed in the next class. Please be tuned for the next class, and it will be very interesting to join the next class, and these topics will be discussed in the next class. These are my references I have taken from this Robert Nelson and the Professor A.K. Ghosh from IIT Kanpur NPTEL lecture. I have combined this. Okay, thank you very much for this joining this my class, and we will see soon in the next class. Okay, thank you very much for joining the class.
Like, share and subscribe. Hit the bell icon for more updates.